Good evening. I'm Tim O'Shea, the Principal and Vice-Chancellor of the University of Edinburgh. It is just an enormous pleasure to introduce you to this audience with Peter Higgs, but it's not just Peter, it's Peter and three subsequent generations of Edinburgh physicists. The University of Edinburgh was all agog on the 4th of July when we were all, well, some of us were lucky enough to be at CERN, the others were pretty much all watching it. And when we had the wonderful outcome of the discovery of the Higgs-like boson. It's really quite a long story. Peter made his original prediction in the mid-60s. I can remember as a research fellow in the mid-70s, Peter coming and talking in the School of Artificial Intelligence and telling us, and I think we pretty much divided between those who didn't understand him and those who didn't believe him. And then it became, about 10 years after that, it became apparent that one could actually build a device to test this. And Chris Llewellyn-Smith, the wonderful director of CERN, started us on that track, and then it became possible. Then the thing was constructed, and then, my gosh! But what a long journey! What an exciting one, and what a really inspiring one. So we're going to tackle this discussion from 4 different points of view, but obviously the key point of view is Peter Higgs, and it's an enormous pleasure for me to ask him to talk to you. Peter.
Well, I'm sure that most of you will be aware of the discovery claim which was made by CERN almost a year ago. And that was a claim to have discovered a particle which was drawn to the attention of the theoretical community 48 years earlier. Maybe it seems a bit strange to have the theoretical prediction of something so far ahead of experimental verification, but it's a sort of thing which has happened before in particle physics. If I go back a very long time, more than 80 years, Paul Dirac predicted the existence of antimatter around 1930, and he was rather lucky. The anti-electron, or positron as we now call it, was discovered by the experimentalists only a few years later, and that perhaps saved him from being thought a crank. Around the same time, Wolfgang Pauli, predicted something which became known as a neutrino because it seems very strange that energy wasn't being conserved in a kind of radioactive decay called beta decay. Pauli had to wait 25 years before the neutrino was actually found experimentally because it's something which interacts only very weakly with other matter, and it took a long time for it to be possible to make the discovery. In my case, it's been 48 years, which is even longer. And what I'm going to try to tell you about the history is that although the particle is associated with my name, my own association with it is really not much more than being the person who most obviously drew attention to its existence in the kind of theory which was being discussed at the time. Now, let me set the scene in terms of what kind of theory we're talking about. If you go back to 1905, Albert Einstein postulated that light, that is electromagnetic waves, as described by James Clerk Maxwell, delivered their energy to electrons in metals in quanta, in discrete lumps, which we now call photons. And that was the beginning of the ideas of what we now call the quantum theory of fields. It was another 20 years before quantum mechanics as a branch of theoretical physics was really developed mathematically. And shortly afterwards, Paul Dirac, one of the founding fathers, showed that the new quantum mechanics applied to Maxwell's electromagnetic field did indeed result in the appearance of quanta, that is, the electromagnetic energy being delivered in a particle-like way, which we call photons. The quantum theory of fields then, with the development of Dirac's relativistic theory of the electron, quantum theory of fields developed in the form of quantum electrodynamics, the combination of Maxwell's electromagnetism with Dirac's electron theory. And after some little difficulties with how you calculate to high orders in Planck's constant in this theory, by 1950, this theory was so successful that it was beginning to make predictions which outpaced the experimental evidence in terms of the fineness of detail. But then when it came to the other forces of nature, the story was rather different. Already by 1930, it was obvious that there had to be another kind of force, which we call the strong force, to hold together the electrically charged particles which make up an atomic nucleus, together with other neutral ones. And there was also another kind of force which we know as the weak force, which was responsible for mediating a kind of radioactive decay called beta decay. That was the context in which Pauli had postulated a neutrino. When the methods of quantum field theory were applied to these other forces involved in elementary particle physics, it didn't seem to work. And we now understand the reasons why. In the case of the strong interactions, it just didn't give any reasonable agreement with experimental measurements. It was not until about 1970 that it was realized that essentially the wrong assumptions were being made about what was elementary, that neutrons and protons in the nucleus aren't elementary, they're made up of quarks. The weak force was a tougher problem because it wasn't just a matter of lack of quantitative agreement with experiment. It was a kind of quantum field theory which gave nonsense if you calculated quantities beyond the lowest order of approximation. In other words, the predictions of things which would be measured experimentally and which must be finite repeatedly turned out to be infinite in the theory, so it was simply no good as a theory. For many years, people in the theoretical community tended to abandon the whole structure of quantum field theory as maybe inappropriate for this kind of problem. And it wasn't until about 1960 that it began to come back into fashion. But when I say fashion, amongst a small minority, including people like me. The person who was responsible for this was a Japanese-born theoretician, Yoichiro Nambu, at the University of Chicago, who noted certain features of the successful theory of superconductors, a very different kind of physics, apparently from elementary particle physics. But superconductors have remarkable properties. The oldest ones known have been metals and alloys at very low temperatures. And at these very low temperatures, they lose all their electrical resistivity. And it turns out that the electric current is carried by something which we would now identify as being a Bose condensate. I'll maybe come back to saying what that means. But the feature of Nambu's work on superconductivity was he recognized the role of broken symmetry, the kinds of symmetry for quantum systems which go beyond the ones which we know of in terms of ordinary geometry, and broken symmetry in this more general sense was a feature of the successful theory of superconductivity formulated in the 50s. So Nambu thought that perhaps this kind of theory turned into relativistic quantum field theory could do something for the forces in elementary particle physics. He applied it first to the strong force. He had a theoretical model, in which protons and neutrons were put in as elementary objects, and there was a symmetry which, if it had been preserved in terms of the phenomena, would have ruled that these were massless particles, which of course they are not. But as a consequence of broken symmetry, which in this theoretical context means that the state we call the vacuum, in which there are no particles, the vacuum state, the lowest energy state, is asymmetric, and this asymmetry then permeates through to all the things which you observe about the particles that the theory describes. This feature could, in his model, generate the masses of particles like a proton and neutron as a consequence of interactions in which the underlying symmetry was manifestly still there. That may seem like a contradiction, but it's how it actually works for condensed matter systems. The problem with Nambu's theories, his theoretical models, which was that they also predicted particles which couldn't possibly exist. They predicted particles with no spin and no mass. And these looked rather like things which particle physicists call pions, but they were massless, and they seemed to be necessarily massless in his kind of theory. This was a disaster because such particles would have been already detected and known to have zero mass if they existed, and they had not been found, and they would have really made a mess of our understanding of the energy generation from stars, because they would be very easily radiated. So that theory seemed to be on the rocks, and that's what was true by around 1962. In fact, a theorem was proved. The theorem is known as the Goldstone theorem, because Goldstone conjectured it, and it was then proved by Salam and Weinberg, which said if you produce symmetry breaking in this way by the asymmetric properties of the lowest energy vacuum state in a relativistic quantum theory, then you must have these massless particles. The debate about that went on in the literature for a year or two, and it was finally resolved in 1964, which is the date you find assigned to the the work which I and 5 others did. It was certainly not just me. There were 3 groups of people involved. 2 who published first were Robert Brout and Francois Englert in Brussels. There was myself in Edinburgh, and then a little later there were Jerry Guralnick, Carl Hagen, and Tom Kibble at Imperial College. And we all published papers which resolved this difficulty of the Goldstone theorem. My own insight was to see that theories which involved an interaction in the right place of the type of the electromagnetic interaction, in other words, Maxwell field, actually evaded the axioms which had been used for the mathematical proof of the theorem. So at the time I wrote 2 very short papers. The first one was extremely brief and simply pointed out the loophole in the mathematical theorem, and that was accepted by the European journal Physics Letters, whose editor was based at CERN. And then the second paper to follow it up was one in which I wrote down the simplest theoretical model I could imagine, which illustrated this point which I had made. That model has become known as the Higgs model. The second paper was rejected. And I heard afterwards from a colleague who'd been working at CERN at the time that the people on the theoretical corridor didn't see the connection of what I'd done with physics. And when the rejection came back, there was a kind suggestion suggesting I should do a bit more work and publish in a certain well-known journal, which at the time didn't have a refereeing system. So that was rather an insult. So I rewrote the paper. The paper at the time of the first version was probably no more than a side of A4. I added a couple of paragraphs, and it became maybe a page and a half of A4. And amongst the extra paragraphs was one in which I said it's worth noting that theories of the type discussed here include the prediction of incomplete multiplets of spin 0 and spin 1 particles. The spin 0 particles were reference to what subsequently became known as Higgs bosons. That's not the end of the story. The second version was accepted by the corresponding journal, the other side of the Atlantic, Physical Review Letters, and the referee, who had also refereed the paper by Brout and Englert, was Nambu from Chicago. But it still didn't really make contact with experiment, because it was still a theory in search of the right application. We all at the time thought it would work for the strong force of particle physics, but that was a mistake. And it was Steven Weinberg and Abdus Salam, 3 years later, 1967, who recognized it was appropriate to deal with the weak force that way. And finally, in 1971, 2 Dutch theorists, Gerard Hooft and Tini Veltman, showed that the theory was mathematically viable for calculation. It wasn't a sick theory. It took several more years before the experimental evidence was favorable to the electroweak theory, which had been formulated in 1967. And by 1975, when LEP, the first collider at CERN, was being planned, John Ellis, Mary Kay Gaillard, and Dimitri Nanopoulos at CERN wrote a paper called The Phenomenology of the Higgs Boson, in which they analyzed how it might be found. The last paragraph says, we do not want to we do not want to encourage a big experimental search for this particle, but we feel that experimentalists who are on projects which might be vulnerable to its existence should keep their eyes open for it. And I think at that point I shall hand over to the rest of the panel to continue the story.
Thank you very much, Peter. Peter joined us in 1960. Alan Walker joined us about 10 years later, has served with tremendous distinction in physics at Edinburgh, and a key part of his role has been the public understanding. Now, I think it's probably, looking at you, totally redundant. You probably don't need a few minutes having some elaboration and some explanation, but I have seen Alan explain, I'll reconceptualize you as 11 and 12-year-olds, and I've seen him brilliantly explain to those. So, Alan, please.
Thank you very much. You'll notice the subtitle under the Higgs boson. I'm supposed to make all that much more easy on you. But I'm going to start with the ancient Greeks because they're the ones, the philosophers there, who asked, if I take a grain of sand and I keep on dividing it, what will we get? Will it still be grains of sand all the way down? And their philosophy was that no, it won't. You'd actually reach something called the atom. Actually, we'll find out that we as modern scientists actually stopped too soon, and we'll find that the atoms are really not, that we know of now, are not the smallest things that we have. The reference to the Athens of the North is that's where you are. We're in Edinburgh, and if you look at the National Monument, it looks a little bit reminiscent of ancient Greece, and that's where we are. And this is the adopted city of Peter, and it's also the adopted city of myself. And even Victoria has come back to work with us in Edinburgh. So, what we know about atoms, which are not the smallest thing, as we'll see, is that they're pretty small. They're 10 to the minus 10, and we have to tell you that in ordinary language, so that's 10,000 millionths of a meter across, so that they're pretty small. And if you look at the size of you, I'm sorry, that's not a comment about you, you actually realize there's an awful lot of atoms inside of you. The electron was discovered, that's the outer orbiting parts of the atom, by J.J. Thomson. And J.J. Thomson, just in case we have that question later on, wrote on the wall of the Cavendish laboratory, "God bless the electron, may it be of some use." So I don't have to justify what we do anymore, right? But the electron orbits around a nucleus, and Rutherford, by scattering alpha particles from gold foil, likened it to a cannonball being reflected by, or an artillery shell being reflected by a paper tissue. And it was such a surprise, and the answer to that was that there is a very hard center to the atom, which is the nucleus. And that's 100,000 times smaller. So actually, if it's 100,000 times smaller than the atom, hey guys, you're mostly made of empty space, if you want to think of it in that way. Most of the mass that you're made of, and we'll come to that obviously, is actually in the nucleus, because the electron is quite light in comparison. If we scatter electrons from atoms and then nuclei, as we increase the energy, we can probe the structure inside the nucleus. And what we find with these experiments is that inside there are protons and neutrons. Are they the atoms of the Greeks? No, they're not, because actually if you fire in electrons hard enough and long enough, you find that there's stuff inside of those too. And you can see on the diagram here, and I've given you a crib sheet on so you can look at it more closely and you can do your homework when you leave, is that you can see that the proton is made of what we now know as being 3 quarks. So the constituents of the nucleus, as we peel back that layer of the cosmic onion, inside there are quarks. And a proton is made of 2 up quarks and a down quark. And a neutron, which is the other constituent of nuclei, is made of 2 down quarks and an up quark. So, actually, that's what ordinary matter is made of. And so, you are all made of up and down quarks and electrons and the force carriers that go between them. And that's what you're made of. And this is ordinary matter, so you're made of ordinary matter. As we'll see, you have no charm, you have no strangeness, you have no top, and you have actually no bottom. Okay, but we'll come to that in time. Sorry, gone the wrong way. In order to understand what Peter did, we have to take another great Scottish physicist hero, James Clerk Maxwell. And amongst many other things he did, he wrote down these equations. Well, actually, he didn't. They were written down in quaternionic form. And these are the form we recognize today that were written down later by Heaviside. Be careful, the Maxwell Society may be listening. But these equations have a solution, which is that there are electromagnetic waves. And what you're watching there, in the vertical direction, you can see the red arrows, that's, say, the electric field. In the horizontal direction, there's the blue arrows, that's the magnetic field, and they're at right angles to the direction in which the wave is propagating. That is what is predicted by Maxwell's equation, and the constants in Maxwell's equation, when you work them out, turn out to give you that the velocity of these waves is actually that of the measured speed of light. And you can read his treatise and you can see those actually connections being made. So electromagnetic waves from Maxwell clearly are one and the same thing, that light itself is an electromagnetic wave, and so great prediction, radio waves and so on. And Heinrich Hertz, again, another statement, discovers radio waves and says, radio waves will never be of any use to mankind. Okay, that's the price you pay. Eventually, we get proved to be right. But the important point about this is that the electromagnetic wave has an electric field which is perpendicular to the direction of propagation. So this is what we actually look at. So if the wave is traveling in this direction, the electric field may be this direction, or possibly in this direction. And what I have with me, I brought, at great expense, some Polaroid film. You are familiar with Polaroid film, those of you out there with expensive sunglasses. If you look, the light is shaded, but light is getting through. What it's doing, it's only allowing light through. Well, I don't know which is that way or that way, but let's take it that the long edge is allowing the light through where the electric field is actually in that direction and propagating through that. And this is cut from the same sheet, so the long direction is where the electric field goes through. If I put them over the top of each other, the light goes through. Of course, now the party trick is to do this. And what you see is one lets the electric field through, which is in the horizontal direction, and the other one will only let it through if it's in the vertical direction, and no light gets through. What it's demonstrating is that light has two forms of polarization, two freedoms, we might say. Now we're going to look at what happens to light when we actually write a quantum theory. That's what we've just seen, so you can see what I've just been demonstrating if you're watching the PowerPoint at home. If we actually now cut to this, I can also produce waves where the electric field rotates around the direction of propagation. And so we can have left-handed and right-handed polarizations, that's right-handed, and left-handed circular polarization. So in this sort of wave, if you think about the quantum nature of light, where photons are traveling along with the wave, so you can see that we can associate with the particles of light some angular momentum or spin. We may come back to that. Photons travel with the speed of light, In the theory of relativity of Einstein, that means they have to have no mass whatsoever. So the characteristic of a massless particle, it can only spin in these two directions, at least a so-called vector particle, one which has some spin. Now let's go forward to the days of the Large Electron-Positron Collider, where we're actually colliding electrons. And as Peter mentioned, Dirac discovered there was an antiparticle, the positron, or the anti-electron, and collide them together. So what we've got in this diagram is electrons and positrons actually scattering from each other. And what we understand about how that process works at the quantum field theoretic level is there's a force carrier between them. The symbol gamma here refers to the photon, the particle that's exchanged in this scattering. Now, this theory is based on an underlying symmetry and also the exchange of a massless particle. And this theory, therefore, is what we call a renormalizable gauge theory, but what it actually means is, as Peter said, is that this theory is calculable. This theory, when you actually calculate to all orders, you can actually make predictions. And if we make predictions, for example, a subtle effect in the spectrum of hydrogen called the Lamb shift, we can calculate that theoretically to a part in a trillion, and we can actually measure it, and they agree. And I think that's a fantastic achievement for a theory that you can actually make predictions and get experimental agreement at that sort of level. So there's a tick for quantum electrodynamics, as it's called. Here's a theory that works, and people got their Nobel Prizes. Feynman, Thomann, and Schwinger get their Nobel Prize for actually this theory. So that was a field theory that worked, but then field theory goes out a little bit out of fashion. So I'm going to jump over the era in which Peter was working. By the way, that's Feynman's quote about how accurate this theory is. It's as though you're measuring from LA to New York to within the thickness of a human hair. Sorry, we're going the wrong way. No. That explains, therefore, if you like, the outer structure of the atom in terms of the force, and we can do those calculations. But the inner structure of the protons and neutrons we now discover are made up of 3 quarks. And we can actually, in our accelerator, when we're colliding together, make other particles. There's a short list here of baryons, as we call them, and they're made up of 3 quarks. And we can make heavier quarks in our experiments, but all of the particles that we see, the composite particles we produce in our accelerator, are either a grouping of 3 quarks, or if it's an antiparticle, 3 antiquarks. We can also make mesons. Peter mentioned pions. Well, pions are made of a quark and an antiquark pairing. And so we can actually also see those. So all of the particles that fill up our telephone directory of particles are actually made up of either 3 quarks or a quark and an antiquark. Now, of course, we don't only just get up and down quarks, we have other quarks too. So our experiments tell us that this is, if you like, the matter part of the standard model. If you look on your sheet, you'll find the section that includes that. And what we have on the right-hand side is the quarks. The shaded part is the up and down quarks, which is what we're made of. The charm and strange quarks can be produced. We sometimes see strange quarks, or if you like, particles with strangeness in cosmic rays. And then we can actually make even heavier ones, the top quark and the bottom quark. And if you look at your sheet, you will see that there's a very massive hierarchy of masses involved in there. These things weigh very, very differently. And on the other side, we have leptons. These are the ones that only take part in the weak, or if they're charged, in the electromagnetic interaction. And we have electron, a heavier version called a muon, and the tau. And muons were routinely, we actually see as being very penetrating particles produced in cosmic rays. If you're to stand in my cosmic ray doorway, then you will know when a cosmic ray and muon has passed through you. In other words, you are knowingly zapped by a muon. It's that shaded area which makes up normal matter, what most of the universe is made of. All of those other particles were probably there at the beginning of the universe, along with their antiparticles. So they're the matter particles. Let's now concentrate on what binds the up and down quarks in to make the protons and give them such stability. There is a very similar theory to quantum electrodynamics, which has exchanged particles which make the quarks stick together. So in our whimsy, we call them gluons. So these gluons glue the quarks together, but the theory is very much more complicated because gluons can interact with each other. And as a result, this is a pitch perhaps to the principal, we need big computers in order to be able to do these large calculations in quantum chromodynamics. If you want an analogy, if you had a black and white TV and a color TV, they work on the same principle, but a color TV is much more difficult to fix. Okay, so that's the way to see these theories. So you can calculate successfully, and the great success of quantum chromodynamics is in the situation where you're actually fitting what's going on using this underlying strong theory, is that these particles being exchanged are intrinsically massless, the gluons are massless, and the quarks, actually the masses, because we never see free quarks, are actually fitted by these programs. So quantum chromodynamics is a strong force carried by the massless vectors called gluons, and it works. So we're getting the theme here. If we have an underlying symmetry that's a gauge of this gauge type, and the particles that are exchanged are massless, then the theory works. And then, as Peter alluded to, we reach the problem. Now, this was not a problem that Peter was trying to solve, and we'll come back to that in a moment. But here, in the weak interactions, what we can think of is, for example, in a nucleus, a neutron changes into a proton, and it emits an electron and a neutrino, so-called neutron beta decay. That's either inside a nucleus or for a free neutron outside. If we actually want to see how that works in terms of the constituents, what we see is, for example, a down quark turning into an up quark. That means charges change, and the particle that then is emitted is, in this case, negatively charged if it's traveling away, and that then decays into an electron and a neutrino. But we know from the characteristics of the weak interaction that the W particle here, there's also a W plus and a W minus, that those W particles have to weigh 90 times the mass of the proton, so they're extremely heavy. So here we have a theory where we have these very, very massive particles, force carriers, and what we'd really like is that they were massless, but unfortunately nature is not like that. It turns out that we also need a neutral partner of the W's called the Z0, and so we need 3 massive force carriers for this weak interaction, or we should probably call it electroweak interaction. And it doesn't work if you just simply stick into the theory the masses by hand. So can we actually keep the symmetry underlying, but give these particles masses by some sort of hidden symmetry? Sorry, that's the force carriers. So at this stage, we need to know how to give the W's and Z mass without actually spoiling the calculability of the theory. And that was a real problem. Although Peters admits he's not addressing that problem, they're trying to solve the strong interaction. And here's, if you like, the original Blackboard equations that we have from Peter. What I just want to point out is the Greek letter phi, if you recognize it, is to do with the Higgs fields. And the letter A, and by the same token the F, is actually to do with what would be a photon-like field. Now, I call it photon-like because this model is going to make this thing heavy, and photons are not heavy. And so what we get is a theory which has that symmetry, but which is broken. And I want to explain that by a collection of crockery I have over here. So I'm not allowed to do any commercials here. So what we have here is a bowl, and you can see that if I was to rotate it around, then it looks the same whichever way I rotate it. There's no change there. If I was to put a particle in there, okay, carefully stuck down with blue tack for our demonstration purposes, if I rotate the bowl, it sits in the center of that bowl. The symmetry, the solution for the lowest state, that's where the bowl rests, in fact, is symmetric. If, however, we change the same symmetry, but we change some signs in the potential, what we see, if we can get this to look right, is you'll see a bowl which has the shape of a Mexican hat. Okay. Or if you like, and you prefer it, the bottom of a wine bottle. Now, if I to turn that round, the symmetry remains the same. But if I now put the particle in, and it stays, it chooses one particular place to sit, because that's the lowest place, so it has plenty of places it could choose to go to, then if we turn this around, it looks different, because the direction in which the particle is changed. So what we've got, essentially, is that the lowest energy state, what we call the vacuum state, is actually now no longer has the symmetry of the underlying potential. The theory has been spontaneously broken, or the symmetry has been spontaneously broken. I'm going to try and explain it. It's difficult to do this, but if I was to allow a ball to oscillate from the sides, okay, it's not, we can't get this perfect, and so on. But what you see is there's a mode of oscillation which is side to side in the trough. There is also a mode of oscillation which is difficult to simulate in here, where it goes around freely. There's no oscillating motion here. In fact, we can demonstrate this better if we take a rhubarber, a very large rhubarber baking dish. Okay, so if we look at this, I can set this rolling. Sorry, let's try another one. And you imagine that if actually it was just sitting in there, it could freely rotate around there, and essentially that is our massless Goldstone boson. So what we got in this dish here is a mode where it goes around, as it were, more like that one, and an oscillating mode at right angles to it. So what we've got, essentially, therefore, is we've broken the symmetry. The underlying symmetry remains the same, but the modes of oscillation now are very different. And the one that actually is going around the trough is essentially, in our quantum field theory, the Goldstone boson. And we don't want that, because there are no massless, spinless particles in nature that we know of. Okay. So what do we do if we're trying to address this question? Because what Peter's model does, what happens is the two modes of oscillation, or if you like, the 2 degrees of freedom of the original massless photon-like object, swallows up that Goldstone theorem, that Goldstone boson, which makes it the third direction of spin, and anything that's massive in a vector particle has 3 directions of spin. But there's something left over, and it's that mode of oscillation around the sides of the trough. And since it's oscillating up and down, and you have to push it up and down, it clearly is something that's a massive mode, and therefore that's what is the Higgs boson. So that would be a model. Peter's model would give a photon-like object an extra degree of freedom, so it would become a massive vector particle, but the price you pay is having over a massive Higgs boson left over. Now, in the weak interaction, we want 3 of those objects. So we have to do some counting. So what we have to do is to start with massless W plus minus and Z0 and a photon. As with the photon, it's got 2 ways of spinning, or 2 polarization states. So we have 8 components there. We have to introduce 4 Higgs fields, 1 positively charged, 1 negatively charged, and 2 neutral ones. And we use that mechanism where the Goldstone mode is swallowed up to make them massive, and that 3 of them are swallowed up to make the W minus W and Z massive and leave the photon massless as nature has it. Okay. Now, we start off with 4 massless particles with 2 degrees of oscillation, as it were, that's 8, and we have 4 Higgs field, that's 12. And after we've done that, we have 3 massive vector particles, the W plus, the W minus, and the Z, and 1 massless photon, And then what we can do the counting, we have one left over, which is the massive Higgs boson. And we have still the same number of fields we started with. The symmetry is still there, but we've actually now found a way of giving things mass, namely the force carriers that we need to give mass, but we have to pay the price because in this particular theory, there has to be one leftover Higgs boson. And that's the standard Mosel Higgs boson, as predicted. Now, before Victoria comes, we have one more little demonstration. What we have to think of is that this Higgs field somehow or other interacts with these particles in order to give them mass. So there's an environment in which the particles are moving, which some couple to and some don't, and some get mass. And I want to illustrate that with an analogy which got nothing to do with the Higgs mechanism, but might actually make it there. And I'd like you to welcome Ida Cumming, who's come all the way from Turin this evening, and she's going to help me with my demonstration. So a round of applause for Ida. So, welcome. I gather you wrote an essay on the Higgs boson over in Turin in Italian. Il bosone de Higgs? Yeah? Yes. Okay. Okay, right. You can write another one now. Okay. I've given you two cylinders there, and I want you to feel them and think if there's any massive, sorry, wrong word, any real difference between them. They look pretty good. Okay, I'll test your physics now. If you were to hold them out, so you hold them by the ends, okay, if you can. So if you hold them like that, between your fingers, that's it, and like that, okay. On the count of three, I want to drop them. Now, what's your prediction? Will they hit the floor at the same time or not?
Yes, if I let them at the same time.
Yeah, that's great. Well, let's test it with the experiment. 1, 2, 3. Great stuff. Okay. Now, I want you to look through these tubes and tell me if there's anything inside. And there's nothing up my sleeve, honestly. I want you now to drop these through the tubes, okay? Again, on the count of 3. So I'll hold them out so everybody can see. 1, 2, 3. You promised you'd let it go. Ida, thank you very much. Those of you out there in the know will know exactly what's going on here, and if you don't, you can think about it later. The point being is that in the environment without the aluminium tubes, these two things fall at the same rate. Whereas in the tubes, one of these interacts with the tubes, interacts with that environment, and there is an effect on it. And if you like, the top quark, for example, being the heaviest quark, interacts more strongly with this Higgs field environment than does, say, the up or down quarks. Also, the W plus and minus and Z get mass by that interaction, but the photon doesn't interact with that environment and doesn't. So, if you like, the secret of the mass that goes to these elementary particles, now this is very important, the elementary particles comes from this Higgs mechanism. To pay tribute to my QCD colleagues, most of the mass of the nucleus comes actually from the energy of interaction of the gluons and the quarks. The mass of a nucleus does not come solely from the Higgs boson. It's only perhaps a few percent. It's these elementary particles in that table that gain their mass, apparently, according to experiments, from the Higgs boson. Thank you very much.
So the university is tremendously proud of Peter's theoretical work. They're tremendously proud of the wonderful work Alan does in explaining to all sorts of audiences about physics. But we also can take immense pride in the actual experimental work that is being done in CERN. We have 35 staff and students who are based there. If you've been to the Taj Mahal and you've been to the Great Wall of China and you haven't gone to CERN, well, you've really missed a trick. The Large Hadron Collider, I had the pleasure of going there with Peter and Alan just after it was switched off in the autumn. It is an astonishing feat of engineering, has got some wonderful scientists, including Edinburgh scientists working there, and a key one is Dr. Victoria Martin, who will tell you about the actual experimental work.
Yes, so I'm going to tell you about how we experimentally validated Peter's prediction that he made now 49 years ago. And so now you all understand what the Higgs boson is. Maybe you'd like to make your very own Higgs boson. So I have a simple recipe that maybe you can try this evening. So what you need to do is you need to take two very high energy protons. I personally get mine fresh from CERN, but any source of high energy protons that you know about will do. And you simply smash them together. And then 1 in 100 billion of these smashing together, of these collisions, will form a Higgs boson. So pretty simple. Unfortunately, your Higgs boson is going to decay. And it decays in what we call 10 to the minus 22 seconds. That's 10,000 billion billionth of a second. So in that time, I'm afraid you don't have time to see the Higgs boson. But no worry, what you can do instead is do what I did with some of my colleagues and assemble a highly sophisticated state-of-the-art detector around the collision point, around the point where you've collided your two protons together. And then you simply observe what the Higgs boson has decayed into. So instead of seeing the Higgs boson directly, we see what it has turned into. And then finally, you just need to do that 25 million times a second for about 1.5 years, and you too can observe the Higgs boson. So let me tell you in a bit more detail how we actually do that. And as many people this evening have already mentioned, Peter and Alan have mentioned, we do it at CERN. So CERN is the European Organization for Nuclear Research. The acronym there comes from the French and not from the English. And it's located at the Franco-Swiss border just outside Geneva in Switzerland. CERN itself is a collaboration of 20 European countries, including the UK. And CERN itself has about 4,000 employees who work for CERN. But what I am is one of 10,000 visiting scientists, and also Francisca here is one of 10,000 visiting scientists and engineers from around 600 universities and research facilities all throughout the world. And of course, the University of Edinburgh is one of the research facilities that works at CERN. So what CERN do for us? CERN is my laboratory. CERN is the European Laboratory for Particle Physics, and it provides particle accelerators. It provides us high-energy protons, other kinds of high-energy particles that we'd like to do experiments with. Currently, running at CERN, there are 23 different experiments. I'm sure a lot of you have heard of the Large Hadron Collider, and that's where my experiment sits. But it's not just the Large Hadron Collider. There's a lot of different work in physics going on at CERN. However, for the Higgs boson, we use the Large Hadron Collider. So let's talk a little bit about CERN's Large Hadron Collider. So we often call it the LHC for short, and it is CERN's main activity, which is probably the reason that you're here this evening. So there's 7 experiments of the 20 or so I mentioned before that use the Large Hadron Collider. And the Large Hadron Collider is actually a chain of different, different accelerators that are shown here. So instead of the protons just going straight into this big ring here, they actually go through all of this structure first. They come in here, they go around this little accelerator, then they go into this bigger accelerator. This is the proton synchrotron. they go on this red line up to the SPS, that's the superproton synchrotron, and that's the accelerator I used back in the 1990s when I was doing my PhD here at the University of Edinburgh. But from then, they go into the LHC, the Large Hadron Collider. And as you might be able to see, there are 4 experiments that I've put there on the Large Hadron Collider. I said there's 7. There's 4 big ones and 3 little ones. So the big ones, you can see, I'm on the wrong slide. Down here is Atlas. That's the experiment that I and Francisca work on. There's also over here one called Alice. At the back here we have CMS, who are another experiment that were instrumental in finally discovering the Higgs boson. And finally, if I can find the cursor, down here we have LHCb. And the University of Edinburgh also work on the LHCb experiment. Now, the whole purpose of the Large Hadron Collider is to collide protons. So even if you have an accelerator, you need some protons. So protons aren't actually that hard to get if you're a scientist or you have access to a scientific supply store. All you need to do is go off and buy a bottle of hydrogen. So in the bottom left picture there, the red bottle is a bottle of hydrogen. That costs probably about £200. That's not very expensive. And the reason that we use hydrogen is a hydrogen atom, a hydrogen gas atom, is made of a proton and an electron. And then if we apply an electric field to that, we can separate the proton and the electron. So all of the protons that we use at the Large Hadron Collider simply come from a rather cheap bottle of hydrogen. So the LHC is what CERN built for us, for the particle physics community throughout the world. And it really is an engineering marvel. So I'd like to take you through a few facts and figures. So the picture that you can see there is an aerial shot over the CERN campus, and the red line you see is the imprint of the Large Hadron Collider going underneath, it turns out, the French-Swiss border. So the Large Hadron Collider is almost a circle, not quite, but almost a circle. It's 27 kilometers in circumference, and I looked that up today just to check. That's 17 miles. And so the protons go around this 27-kilometer ring, and they do this almost at the speed of light. The LHC itself is underground, so if you go off to Geneva, you won't see a big red line on the ground as much as we'd like to paint one for people coming in to land at Geneva Airport. It's 100 meters underground. And so the tunnel was actually built for a previous accelerator, the one that Peter and Alan have mentioned already, called the Large Electron Positron Collider. And the picture you can see there in the top left is when they were doing the tunneling in the early 1980s. That's the tunneling machine breaking through. To keep the protons going around that 27-kilometer ring, we use magnets. And there's 9,300 magnets that are used to keep the protons going around that orbit. Now, the workhorse of the LHC in terms of the magnets are called dipole magnets. And there's 1,232 of these dipole magnets. And the picture that you can see there of the blue tube is one of the dipole magnets. It's being lowered down from the surface 100 meters to be placed in the LHC tunnel. So this is when they were installing the LHC in mid-2000s. Each of those dipole magnets is 14.3 meters long, and apparently the clearance in that shaft where it's coming down is not very much bigger than 14.3 meters. They are run at a very, very cold temperature, just 1.9 degrees above absolute zero, above the coldest temperature that you can physically obtain. And to do this, we use liquid helium. They cost quite a lot of money each. So it's half a million Swiss francs each, which turns out to be about 350,000 pounds each. And what's more, inside each of those is ultra-high vacuum. So this is a picture of inside some of the LHC magnets, not the dipole magnets. These are some of the other magnets that we have to use. And you can see, I'll see if I can show this to you, there's two holes, one here and one here. And there's two holes because we need two sets of protons. We need one set of protons going that way and another set of protons going that way to go around the racetrack before they collide. So that's our protons that we need. And then, of course, you need a highly sophisticated detector. So here's a picture, an artist's impression now, of the ATLAS experiment that Francisca and I work on. It's this little piece here, and you can see where it sits on the LHC proton racetrack, and also the shafts that go down there. You may have be familiar with this picture of ATLAS. This was taken once when ATLAS was under construction, and what you see there, the main structures that you see there, there's 8 of them kind of spreading out, are 8 giant magnets that we use as part of the detection system. Now, if you went to see ATLAS these days, it's actually full. So there's a picture here when they're filling up that gap of the magnets, they're filling it up with a detector we call a calorimeter. It's called a calorimeter, like calories. It measures energy, which is very important. So ATLAS itself is essentially just the largest and most sophisticated digital camera ever built. It is 45 meters long and 25 meters high. It would fill this entire room that we are in with sophisticated detecting equipment. And it weighs about 7,000 tons. And of course, it's fun to go and see. So I took some of my colleagues there earlier in the year, and you can see that we're all having some fun at ATLAS. This is just the corner, because the cavern is entirely filled with a detector. The only place you can easily get into if you're a tourist is just into the corner. So we're standing there in the corner. And as well as Peter and myself and some Edinburgh colleagues, we also have 2 spokespeople from the ATLAS experiment. So some of you recognize Fabiola Gianotti, who was one of the speakers on the 4th of July announcing the discovery of the Higgs boson. Okay, so now I want to show you how it is with all this beautiful equipment, with a Large Hadron Collider, and with the ATLAS experiment, we actually find a Higgs boson. So here's an animation, and the bright spots there illustrate protons, and you see they'll go through the chain of the CERN accelerators, and as they go through each part of the accelerator, they get faster and faster and faster. So they're in the super proton synchrotron, and now they're in the Large Hadron Collider. So let's focus in and see what's happening inside one of these dipole magnets, and someone's put some graffiti on the wall there. So see, we've crossed the border now from France into Switzerland, and now we're inside the accelerator, and that is a proton with 3 quarks inside. And the proton is going to approach the ATLAS detector underground. And of course, we need another proton for it to collide with, and you see the other proton coming the other way. They collide, and they produce what looks like fireworks. And inside that fireworks, we see these 2 green shining bands, and that's because ATLAS there has detected 2 photons, 2 of the particles of light that Peter and Alan were talking about. And that's what we're looking for when we look for the Higgs boson. So I said that ATLAS is essentially a huge digital camera. And so what we do is we sit there and we take pictures, digital pictures, very high resolution digital pictures of the 2 protons colliding. Now, we don't have any control about the 2 protons are going to do when they collide. We're simply observers. And the question is, in that, can we observe the Higgs boson? So I've already alluded to the fact that the Higgs boson decays, and it can decay into 2 particles of light, into 2 photons. And this is one of the pictures that we've taken with our ATLAS experiment, where we've seen not very much else apart from 2 particles of light. So the yellow that you can see in this picture, at the bottom here in the circle, and the top here in the circle, and down here are some blow-ups in a bit more detail. The green there illustrates the calorimeter that you saw being inserted. And finally, there's a graph showing you the energies that are measured of those 2 photons. And it's pictures like this that are the key to finding the Higgs boson. Now, it's not just 2 photons. The Higgs boson can decay into lots of different things. And actually, one key set of things that can decay into are the Z bosons that Alan talked about. Now, the thing about the Z boson is it actually also decays quickly. It decays even quicker than the Higgs boson. And it can decay into an electron and an anti-electron. So we had a Higgs decaying into 2 Z bosons, and each of the Z bosons decays into an electron and an anti-electron. So I need 2 electrons and 2 anti-electrons. And that's what this picture shows. So this picture shows that we've taken 2 electrons and 2 anti-electrons. So the green and red spikes there are indications that what we observe in the ATLAS detector is 2 electrons and 2 anti-electrons. And finally, I've got a kind of 3-dimensional picture, because it's a 3-dimensional camera that we have. So we take from every viewpoint at once, which I'm now trying to project on a 2-dimensional screen, of another place where we think we saw a Higgs boson. So this time, we also had the Higgs boson. Again, it decayed into 2 Z bosons. But the Z bosons can decay not just into electrons and anti-electrons, but into the heavier relative of the electron that you'll have on your sheet there, called the muons. So here I've found 2 muons and 2 anti-muons. So what we do is we take the pictures, we scan them electronically. In fact, we use graduate students to basically do the scanning. And then we put our data onto a graph. Right, so this is the graph that got us all excited. And let me try and explain why, because it is not perhaps obvious why this should get you all excited. So what is shown here is the mass of the 2 photons. So I remember the Higgs boson can decay into these 2 particles of light. If we measure the energy from the particles of light, we can work out what the mass of the thing was that decayed into those 2 particles of light. And what we see here is, so the black points are what we've measured, and the red line is to help guide the eye. So you can see they kind of fall off. So as we go to higher and higher and higher mass, we get less and less and less of this happening. But in the middle there's a little bump. Now, it does look like a small bump. So the plot on the bottom shows if I take off that kind of underlying behavior, and you can see for sure there's a bump there. It's just a little bump. And the one thing that Peter's theory didn't tell us about the Higgs boson is how heavy it was going to be. So the key parameter we really want to measure to begin with is how heavy is this thing. So the little bump we see is at 125 giga-electron volts. A giga-electron volt is the unit we use for mass, and it's about the mass of a proton. So we see a little bump at about 125 times the mass of the proton. I also told you that ATLAS observes Higgs boson decays to Z bosons, and here's the picture of this. And again, so the red shape is what we expected if there was no Higgs boson. But you see there's also this blue bump. It's the black points that are the data, and the blue bump there is also to guide the eye. But the bump is also there, and the bump's also at the same place at 125 times the mass of the proton. And that's when we all got really excited. So I hope you understand that it's not, we can't just take a few photos and say, oh, that was the Higgs boson, that was the Higgs boson. it takes time. It takes time to see more and more of the photos that look very similar. And so some of our colleagues have come up with this animation, which I will try and now achieve, to show you as we ran the Large Hadron Collider for a year and a half, we took more and more data. And this is running from 2011 to 2012, and you can see the data being collected. But you can see that there's some of the black points there that do not agree with the red. And that's where we think the Higgs boson is being produced. So you can see we've zoomed into that region now where the black points didn't agree with the red, and put in the blue to guide the eye. And this is where we saw the Higgs boson. So it's not something you can do instantly. It's not one photo I can show you and says, this one is definitely the Higgs boson. I don't know for sure each time. It's an accumulation of lots of data and then understanding it slowly. But finally, we've got there. So it's a boson. We're very excited. The universe is full of magical things patiently waiting for us. Sorry, I can't read that perfectly. Patiently waiting for our wits to grow sharper. And that wasn't it. We didn't just congratulate ourselves. We got a very nice letter of congratulation from Professor Peter Higgs of the University of Edinburgh. So I've been talking about the ATLAS experiments measurement, but also our colleagues on CMS. We don't work at CMS and the University of Edinburgh, which is why I've been focusing on ATLAS, but both ATLAS and CMS finally found our Higgs boson, and it was a great achievement. So thank you very much.
So CERN is the biggest and most elaborate scientific experiment in the history of the world. It really is stunning. And one of the things that is immensely attractive about it is hundreds and hundreds of young scientists. And a feature of it, and I don't know whether that's particularly to do with the physics culture, but a feature of it that is really striking is it's a scientific democracy. And all over the place you see groups where you'll have some older scientists, if I put it like this, like Peter or Alan, or even Victoria, and then you'll have and then you'll have lots of younger scientists, often disagreeing with them. And the striking feature is that they're allowed to disagree and come up with new notions. And so we have got some wonderfully promising young scientists there. Francisca is from Chile. She's in her second year of a doctorate. And she's going to tell you a little bit about what it is like to be a young, promising scientist at CERN.
Okay, so I'm Francisca, as you know, and I'm here to tell my story from a student that is doing his PhD. And as you can see, I'm also the last of this fourth generation panel, but we also have a fifth one, as you can see. Maybe, we don't know. So as you can tell from my accent and from my very bad English, I come from Chile, so there on South America, where we have the A letter. From there, we have two universities that are collaborating at ATLAS, and approximately 15 scientists that are working on it. So I did my undergraduate and my master's degree over there. And then I applied to the University of Edinburgh, and I got accepted, yay, to do my PhD. And then I flew from Chile to the UK, to Edinburgh. And it's a really nice 11,791 kilometers. So it's a nice 15-hour flight. I really recommend it, so please go to Chile. But then when I got to Edinburgh, I realized that here we have approximately 20 scientists and 6 nationalities to deal with and to collaborate with, all with the same purpose of this research. And from there, I've been traveling to get to conferences that has to do with my research. I have to travel to Geneva, to CERN, for meetings that also had to do with my research. And then at CERN, I found that we have over 3,000 scientists working all together, also 38 nationalities, and 175 institutions working all together. So for me, it was, wow, this is really, really big. So this is a picture that I wanted to show you about the Atlas collaboration. So you can see that we fill the 5th floor of building 40 at CERN. So we're a lot of people. And also we have the Atlas Particle Physics Experiment Group at University of Edinburgh, and I wanted to show you some pictures. So the upper left picture are the ones that are based at Edinburgh, and the lower picture are the ones that are based at CERN, so working there. So what do we do for Atlas? First, we mainly do Higgs searches. So one of the channels, with the search channels that we work on is the Higgs 2Z2 for lepton, and the other one is the Higgs 2 boson and anti-boson. Other works that we do also to collaborate with Atlas are the simulation. So we basically, whatever data that we take from the detector, we need something to compare with, and this is the simulated data. And finally, we also do some work for the Atlas upgrade. So some of you may know that now Atlas is closed, it's shut down, it's not working, because we need to fix some parts, and also we need to make the detector better for next data taking over the next few years. So I wanted to talk to you about also what was announced on the 4th of July of 2012. So first, we have some pictures. So the upper left picture is the lecture room where the the talk was held. And these other two pictures are on the right and on the bottom is the queue that was the night before the talk. So people will get a seat on the talk on that lecture room there. We even have one of our students that she slept over there during the night, and then she got a seat over there. I think she's like right at the back. In my experience, I was on holiday in Chile, so I was enjoying my holidays. But still, we got together with my ex-supervisor and with my student, with the other students over there, and we woke up at 3 a.m. to see this live. So that was really exciting. So this is just a picture from the paper that was submitted. And what I want to say here is that the paper was about our observation of a new particle. Because at that time, we knew that we saw something, but we really didn't know what properties that did this particle have. So we couldn't say really this is a Higgs boson or not. So we have the lecture theater after this big announcement. There we have Alan, and there is Peter. So we have a Zoom there. So what was said that day? These were the plots shown that day, and what is really important here is that we have the y-axis on this color plot, and what is it telling us? It's telling us about a probability. So every colored line is just showing you whatever we saw on different search channels. And the black curve over there is telling you about the combined. So we put everything on a mixer, and we got the black line. So this is telling you that we have a 10 to the minus 9 probability that whatever we saw is not a Higgs boson. So it's really, really small probability that we mess it up. And the plot on the right is just the black line zooming. I also wanted to show you this extract from the paper that I wanted to read to you. So it says, clear evidence for the production of a neutral boson with a measured mass of 126 plus or minus 0.4 plus or minus 0.4 GeV is presented. This observation, which has a significance of 5.9 standard deviations corresponding to a background fluctuation probability of 1.7 times 10 to the minus 9 is compatible with the production and decay of the standard model Higgs boson. Did you understand something? Me neither, but the point here, very important point, is that we are 99.99995, I hope I get the nines okay, % sure that we found something of 126 GeV mass. So this is also the same plot as Victoria showed you. So basically, it's telling you how we gather all the data from 2011 till 2012. So it was a long time. And you can see again how the signal was appearing from the background that is modeled by the red curves and the purple curve. And there we have a zoom on the signal part of the plot. So some final words. As I already mentioned you, I did my undergraduate and my master's degree back in Chile. And every time that I have had a lecture or whatever, professors told me these stories, or almost like fairy tales, are said to me about these great physicists that did these very big discoveries very far away in time, and etc. So, for example, Maxwell with electromagnetic theory, Marie Curie with radioactivity, Einstein, Professor Higgs here, Carlo Rubbia and Vandermeer with the discovery of the Z and the W boson. And now we have this important discovery of the Higgs boson. And I'm very glad, and I wanted to share with you that it is very nice to be honored with this very, very small role on these stories, and that you can also achieve this and study this and participate on this. So thank you very much for listening.
Thank you very much, Francesca. And I mean, for Edinburgh, one of our important commitments is to go onwards. We've founded a Higgs Centre, and what we want to do with the Higgs Centre is find the new Higgses of the future. I'm very pleased to see one of our key supporters with us here this evening. Now you've got time for some questions. Feel free, you can ask a question to all four, or you can pick out somebody. Do remember to say who you are and try to keep the question short. So first question. Anybody? Please, there's a question here. There we go.
Magnus Linklater, now that you've found the Higgs boson, can we close down the Large Hadron Collider? Does it have any further use?
I'll start by answering this, and if you mind, and say absolutely not. We found the Higgs boson, but we don't know precisely how it behaves yet. The theory that Peter started makes some very specific predictions about how it should behave. And we want to go off and test. We need more Higgs bosons, if you like. We have several thousand, but we need to make more and test exactly how it behaves. And as Sir Tim said, I mean, we're looking for the next Higgs. So we're looking for other predictions of other particles that might exist. And we want to test to see if we can see those at the Large Hadron Collider as well. So I mean, the Large Hadron Collider has a plan to run into the 2020s. Which it can do with a bit of upgrading in TLC. And I do hope that we do that, and we here will still be looking at the data coming in from the LHC for many years to come.
And yes, Alan?
Well, I think it's also important to know that the standard model itself, although it looks in good shape, it seems to be working very well, still has large number of parameters which have to be measured in order to do that. And one of the problems with the standard model, it has a very large number of parameters which are not a priori known. There isn't an underlying theory for why there are so many parameters. So we need to actually get a handle on that, and so we have to do a lot more of the, if you like, the nuts and bolts measurements of those things. But in addition, if we go up in energy, we may start to begin to see, as is planned, things which are giving a hint of things beyond the standard model. And the Higgs boson, if you like, is a piece of the jigsaw But the jigsaw itself isn't that actually perfect in the sense that it itself is an edifice, but it's an edifice built on lots of parameters. And those parameters, if we measure them, we might find deviations which indicate there's something beyond. For example, we really have to understand what dark matter is that we can see out there in the universe. And there's a possibility if we start to see supersymmetric particles, then one of the massive neutral ones of those may well be a candidate for that dark matter. So if we're going to try and see these things coming in from Earth as we have experiments doing dark matter searches, then we want to also be able to produce them in the laboratory, and that may require us to go up in energy. So the Higgs boson, if you like, is the start of other things. We have to do more precision measurements.
I'd just like to add that it's very clear from what we know already, or what we know we don't know, that the Standard Model with a single Higgs boson isn't the end of the story. We just don't yet understand neutrinos.
Yeah, and I'll add my non-physics tuppence worth too. I mean, one of the other reasons for keeping it going is if you've got such a massive piece of scientific engineering done with such tremendous precision, you get some nice side effects. One side effect is the World Wide Web. The World Wide Web was developed at CERN to meet the needs of all the physicists, like the physicists in Chile and in the United States, who needed to be able to connect at any time of the day and get the data. So it was precisely invented there. If you look at modern ways of diagnosing and treating cancer, then you're talking about extremely highly focused beams of positrons. The move from using X-ray technology to using much more powerful and incredibly more precise, that again is a direct consequence of the research that was done at CERN. So there are some really good secondary things, as well as, of course, the exciting hunt. Another question, please. Yes. Here's the microphone coming, yes.
Well, I once read a novel about a book that by a guy called John Connolly, and it's basically a novel mixed with facts and fiction, and there's a lot about the Large Hadron Collider in it. And at one point it even mentioned a machine called the ILC, or the International Linear Collider. Now they had a whole bit about this, and will such a machine ever come into existence in the real world? I was just curious.
I'm not a physicist, but I was at the launch of the technical specification for the International Linear Collider last week. So the non-physics fix is, it's certainly doable. It would cost about twice as much as the Large Hadron Collider. So it might very well be built. But somebody more expert like Victoria can tell you it properly.
The ILC, the International Linear Collider, is a conceptual project, and I work at the Large Hadron Collider, but my secret hobby is to think about if we also need the ILC. It would be a bit different from the Large Hadron Collider. So the Large Hadron Collider collides protons and protons. The problem with protons, you can get them to very high energies, that's great, and that's what we do. But as you saw in that video I showed of the two things colliding, they're made up of 3 little bits, 3 little quarks each. And so when you make a collision of the protons, they're very messy. The ILC would use electrons instead. And instead of being circular, it would be linear, hence the International Linear Collider part. And they make much cleaner collisions. And it would allow us to measure properties, for example, of the Higgs boson much more cleanly. So I think we still have to understand if this is the project that we really want to do, and this is the place we want to invest the money, but certainly we think that we could build it, and maybe in the future, maybe 25, 30 years from now, we'll also have the International Linear Collider telling us more about the Higgs boson, or more about supersymmetry, more about physics.
But it would be very expensive, and this is where people like Magnus Linklater come in. It would, it would cost about, the current estimate is twice as much as what we've already done, which is the most expensive scientific experiment in the history of the world. So we would have to convince the skeptical newspaper people that we really need to do this. Next question, please. Please.
Hi, my name is Claire Dugan-McCallie and I work for STFC, which is the organisation that funds the UK subscription to CERN. Part of my job is to convince governments and funding agencies what the impact of fundamental science is. So, and the web as well, the kind of spin-offs. So could the panel comment on what they think the impact of this discovery will be in 100 years' time, say?
Alan. I already alluded to the fact that people who make these discoveries often don't know what the consequences will be. And it reminds me of the famous quote, you'll find it in Leon Lederman's book, that infamous title, which I won't repeat, where he says that he reports on Richard Wilson, who was the person who was actually to be the director of the to-be-founded Fermi National Accelerator Body, or Fermilab. And the congressman asked him, and tell me, Professor Wilson, what will this do for the defense of the United States? And Professor Wilson said, nothing. And the congressman said, that's not a good enough answer, you'll have to elaborate. And so he said, as with art, poetry, and literature, and other such cultural things, it will do nothing for the defense of the United States per se, but it will make it worth defending. And that's not a frivolous point, is because what drives the people who want to do these things is actually curiosity. In order to actually look at these things, you have to drive the technology to the limit. Often you're building things which you know in principle you should be able to build. So when you go to the inaugural conference where they're discussing the Large Hadron Collider and the detectors, they know what they should be able to do because you know the laws of physics. Thank you to Maxwell and others, that you actually should be able to do that. But the technology that's actually required to make that work is new technology. There are things that just simply happen out of that technology. I've actually had 2 MRI scans which use superconducting magnets, which wouldn't exist if it hadn't been at CERN. And routinely now, the computing that's needed for the Large Hadron Collider led to the formation of the grid. This is a very large distributed computing around the world, but it's not just used now by people doing LHC analyses, but it's actually used for many other projects. So this, if you like, are things that come as a result of pushing that technology envelope. So what's the use of the Higgs? Well, Peter would say, we can see no use for the Higgs in the foreseeable future, if ever. The question is, however, in order to find the Higgs, you have to invent technologies that we all benefit from. And I think that's the point. Either we, as a civilized nation, pursue these big ideas and try and understand the universe, or we don't, and that's the question, is whether we do that. But if we do want to know those answers, then the technology that we push has in itself spin-off, which, I don't think many of these things would have actually happened if it hadn't been for that sort of push for these answers, which are very deep and so on. I'm sure other people want to comment.
I think of the latest technology spin-off that came from the Large Hadron Collider. So I told you when we put the protons inside the LHC, it's in a vacuum, a very, very high vacuum, and they've managed to use that vacuum technology now to make very efficient solar panels, which are now on the roof of Geneva Airport. So at the moment, this is just a small-scale thing, but we don't plan for the impact, but the impact does come. And we can't see what technology is going to be like 100 years in the future, but we need the science for there to be any technological impact. And that we do the science because we're scientists, but we understand and we encourage the technologies to spin off out of that and influence the daily life of people that ultimately fund our efforts.
One other thing that you should realize is that not all the people who go there and do these fantastic job of work, the young postgraduates, for example, not all of them are going to end up with full-time jobs there. People get a fantastic training in skills of sifting through data or pushing technology or understanding technology or inventing things. And then they go out there and they work in high-tech industries. So that actually, if you like, you could regard CERN as a place where there is so much enthusiasm that people are so willing to learn But eventually, some of those people sadly can't stay in particle physics, and they go out and enrich our technology elsewhere.
Very good. And we'll take the last question here.
My name is Guo Chunju from China's Xinhua News Agency. My question is, at this age, could you make any suggestion for any potential sector we can apply this scientific theory to make renovations? And what's the value of the further research investment? And if it does need more investment, is there any estimated amount? Thank you.
I can't do that.
So I can say the Large Hadron Collider, if we want to keep running it obviously it requires electricity, but that's a small fraction of the cost, but we're going to also have to upgrade it. So one thing that's actually going on at the moment as we speak is they're going in and they're welding. Someone told me how many it is. It's like 10,000 joints. There's a welder going in with a welder's mask and welder's torch and welding it. So it does require some money to upgrade it a little and keep it going, but it is a small fraction of the original investment. And in fact, one of the reasons the Large Hadron Collider was relatively cheap, although it was the most expensive experiment ever. But it would have been a lot more expensive if we chose not to build it at CERN, where we already had all of those, the infrastructure, the accelerators, the PS and the SPS that we saw, and also the tunnel. So I think the actual investment in the Large Hadron Collider was about £1 billion, but to build it from scratch would be about £6 billion.
Also, in terms of, you could go out there and find lots of other projects which cost a lot more than that and have larger cost overruns. One of the things that CERN does is that it has a budget, but it keeps to it, and it actually manages to build quite a lot within its budget. There are projects not very far from here which actually couldn't claim that.
We'll stay away from the large trams project. In a moment, I'm going to propose a very short vote of thanks. When you leave, outside there's an exhibition. There are displays of Edinburgh research, and young researchers would be very happy to talk to you about that if you'd like to. The Royal Society of Edinburgh has also, with complete lack of sensitivity, got a display called From Higgs to Maxwell. This is a very insensitive thing to do because, I mean, the similarity of Higgs and Maxwell is very straightforward. They're both great scientists. There is an enormous difference, which is that Peter Higgs was not educated here and we gave him an academic appointment, whereas James Clerk Maxwell was educated here and we refused him an academic appointment. We've had 4 absolutely superb presentations taking us from the theoretical point of view, the public understanding point of view, the empiricist's point of view. Am I allowed to call you empiricist?
I am.
Yeah. The empiricist point of view and the young scientist's point of view. Really wonderful. So please join with me in applauding Peter and his colleagues again.
This production is brought to you by the University of Edinburgh.